In this video, we will discuss rotational kinematics, or motion when objects rotate. Okay, objects rotate. It can be something like this, cars in a circular track. Or it can be something like this, a merry-go-round going round, around, around. Okay. Now, the key here, whenever an object is moving along a curved path, whenever it's not moving along a straight line, there is an acceleration. There is an acceleration because the direction of the velocity is not staying the same. Now, it does not matter if the object is moving at a constant speed or if it is speeding up or slowing down. As long as there is a change in direction, there is acceleration. Now, in general, what we do when we discuss the acceleration of an object that can move in a curved path, we break the acceleration in two components. This would be the total acceleration, A, and we break it into a component that we call radial acceleration and another one that we call tangential acceleration. So if we look at the dashed line as the curved path, and this is our object here, now the tangential acceleration is going to be an acceleration tangent to the dashed path. So in this particular case, is going to have the orangish color. So that's the tangential acceleration. Now, along with that, there will be a radial acceleration, and that one is the blue one here. Okay, that's the tangential acceleration and the radial acceleration. The overall acceleration is the vector sum of both, which is going to be this one. Now, the radial acceleration is equal to v squared over r. It's just the magnitude. It can be shown, it can be derived and shown why it is v squared over r. It can be shown geometrically. It can be shown some other ways. But it is v squared over r in magnitude. The tangential acceleration, we deal with it like we deal with the other accelerations we dealt with in the past. It's going to be the derivative of the tangential velocity as a function of time. So the tangential acceleration is going to be related to the velocity that's along the same path, which is the tangential velocity. And it's going to be the derivative of that. Now, it's often convenient to express this in terms of polar coordinates instead of x and y, I and j. In terms of, and that's because the radial component is along the radius and the tangential component is tangent to the curved path. So if we look at this carefully, the unit vector along the radius is given like this. But the radial acceleration is going to point inward towards the center of that curve. So thus, the radial component of the acceleration is going to be given like this, minus v squared over r. This is the radial component, a sub r. I just realized I put it the opposite order of the formula on top. But a sub r is going to be minus v squared over r. The minus is because the blue arrow, as you see here, is opposite in direction to the red, pink arrow that represents the unit vector for r. Now, the unit vector for theta is going to be tangent to the circle in the counterclockwise direction. That's this pink arrow here. That's our theta. So the tangential acceleration is going to be along this direction, and it's going to be the derivative of the tangential velocity. Okay, so let's look at it in another page. So what we said, the acceleration is the sum of two accelerations, a radial acceleration, sometimes we call it centripetal acceleration as well. So that's why you see the C, and we call it centripetal because it points towards the center. And then a tangential acceleration. So the radial acceleration in magnitude is v squared over r, and the tangential acceleration is the derivative of the tangential velocity as a function of time. And in terms of polar coordinates, that's the way we write it down.